Hey, buddy. It was great having coffee with you the other day, and I promised you a follow-up video to something we chatted about. I'll keep it kind of quick, I think. Anyway, this is the problem that was sent to me a few years ago by a former student, JT, down here. You can see him. And it's you've heard it before. It's a classic problem about how big the number 52 factorial is, and that's where the problem kind of starts. What I end up doing with my students is we develop this game called Woot, which is based on two decks of cards. You face each other and you shuffle them and then deal out the cards one at a time. And if the exact same card shows up in the exact same place with both players, it's called a Woot. You have to yell. If that happens, they have to go whoop, and then it's a fun problem to develop over the course of a day or so because it's counterintuitive. It's counterintuitive how often it happens. Now, there's all kinds of websites devoted to the mathematics of it. As I dug to prove it myself, I stumbled upon something called a derangement, which is actually not just describing how my mind works, but also it's the idea of two random permutations having no objects in the same place of the same size. Two permutations of sets of the same size having no objects in the same place. But it's Math 105. We're not going to prove set theory stuff. So I built a simulator, which is actually kind of fun. And I can send this to you if you want it. I don't know why you would, but if you do, let me know. I'll send it over. And unless I may have already. I may have already sent it to you. I'm not sure. Anyway, it simulates two decks of cards being dealt out in their entirety. So you got deck 1 and deck 2, and then each of these puppy dogs right here are based on random numbers that are hidden over here. This is the kind of stuff I was telling you about I do an awful lot in my classes. I don't have the kids build these. These are pretty intense formula-wise, but I have them interpret them, which I'll kind of walk you through here. So each card is ranked, and the fact that there are suits or ranks in the deck of cards is irrelevant for this problem. What's relevant is the fact that there are 52 unique things. So I have them dealt out randomly across the top of deck 1 and across the bottom of deck 2, and then if they match, you get a little red 0 down here. That's pretty straightforward. You just subtract the two cards from each other, and if it comes up 0, that means they're the same. So as you scroll through this particular arrangement, there are actually two Woots. The card 14 and card 50. Now, if I re-randomize, I get, let's take a look and see if any of them showed up. Okay, there are none there. Re-randomize again. There are none. Oh, there's one at the very end there, card 13. So what I have the kids do is just basically hold down the F9 button, which is the re-randomizer button in Excel, and then it's and at this point, after we've played the game with real decks of cards and we are into the analysis, they're kind of scratching their heads going, how can it be if 52 factorial is so huge that the Woots are happening this much? And honestly, that's beyond the scope of what Math 105 does. What I want them to do is be able to interpret data. Like, for example, there's the cumulative responses. So 64% of the time. And if you keep this going, if I remember correctly from the math I did, the chance of getting a Woot ends up being 1 minus 1 over E due to some really fun limiting factors, which is super rad. But the important thing is get them looking at these graphs. And then I have some other graphs in here that I have them look at too, like how many Woots do we get? Like how many times do we match? It strikes them as odd, and it struck me as odd when I first saw it, that the chance of getting exactly one matched card is the same as getting exactly no matched cards. And these graphs end up spurring a lot of good discussions, especially early on in the term. One day I had a student tell me the chance of 2 Woots looks like it's half of the chance of 1. The chance of 3 Woots looks like it's a third of the chance of 2, and maybe 4 is a fourth of the chance of 3. And when you go in and look at the math of the derangements, he was absolutely correct. So totally awesome. And then where do the Woots occur? Do they occur at card 1? Card 52, somewhere in the middle. So the whole idea of this is to kind of get them thinking about Math 105 from that perspective. Okay, and that's fun. Now, the reason I was telling you the story about my next publication that I want to try to work on is I had a student named Paul Stryken a couple terms ago who said, well, yeah, but what if we ended up using more than one deck each? So he wanted to, instead of going back to the decks and having 52 cards, he wanted to have 104 cards shuffled together. So 2 full decks of cards shuffled together. And I asked him, what do you think would happen? And he said, he's like, I think there'd be a higher chance. And I said, well, I don't think there will be. My gut feeling is saying it's going to be exactly the same because you have the same, you're just replicating, it's a multiple problem. So anyway, we decided to take a look at it. So I created a second spreadsheet. This is the one with the single deck. So this has 52 cards in each deck. And then this one over here is double deck. So this one you have 104 cards mixed together. And they're numbered all the way up through 104. I don't know if you can see those right there. Oh, actually, that's kind of fun. In this particular one, card 104 was the match. And I had to learn some new Excel coding, which was fun. There ends up being a modular arithmetic command, which I didn't know, which makes the problem really easy to code. But I'll be damned if you take a look at this right here. You take a look. It looks like the probability of getting a Woot with 2 decks is about 7/8 instead of about 2/3 with a single deck. So Paul's little gut feeling was that it goes up, and I'll be damned. It sure looks like it does. So my next thought was, well, what if we have even more? So I decided to make another spreadsheet with 3 decks of cards. So now we're going to go out to, what is that, 156 cards, I guess? Yeah, right there. So I said, okay, let's run it and let's see what happens. So here we go. We're going to go ahead and let this thing run, and we're using modular arithmetic to look for hits. And I don't know, this is where my mind got blown right here. Because look at the chance of matching. It's the same as it was for 2 decks. And then I put 4 decks in. I said, what's the chance of matching for 4 decks? And I'll be, God damn! And it doesn't matter. 5 decks, 6 decks, 7 decks. I built some really quick. I didn't have the kids look at that, but I had them analyze this and say, what do you think? Is this surprising to you? Why? Why is it surprising to you? Does it make sense to you? Why? And that's kind of the thing, that I want to track down the math of this and find out what the hell's going on and why this is so weird. I mean, this is mind-boggling to me that these chances are not changing as we add more decks, but they did change when we added a second deck. So I want to dive into the mathematics of the derangements of these multiple decks and find out what the hell's going on, which of course is not what Math 105 is all about. You know that and I know that. But the wonderment of why this kind of thing happens, I think, is. So anyway, I just wanted to share that with you, and I'm happy to send the Excel sheets over if you want. They're kind of fun to poke around with. If I were you, I'd just go fishing. Many hugs, my brother, and I'll talk to you soon.